Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at some mass transfer specific interview questions and answers. And here we're going to look at some of the most common questions that you could potentially be asked in respect to mass transfer and give you fully comprehensive responses that will make you stand out against all the other candidates. So if we take a look at the first potential question is, can you define a mass transfer operation? A fairly straightforward question, but one that you could give a very brief answer or you could provide a fairly comprehensive answer. So in simple terms, a mass transfer operation is one that is carried out for the separation of components within a mixture. So that would be a fairly standard answer. But if you want to go above and beyond, then you could add in some further details on things like it involves the transfer of materials, in which it can involve the utilisation and the differences in, say, the solubilities, the diffusivities, the vapour pressures, and so forth. So you're now providing some additional context to your answer. Question number 2 is, what are the examples of mass transfer within the human body? Now, regardless of what job you decide to go for, whether it's say in pharmaceuticals, whether it's in food, petroleum, you name it, the chances of being asked this type of question is quite high, and it's on the basis that it's testing your overall general knowledge on mass transfer from a practical human standpoint. Because this is one of the day one mass transfer as you talk about stuff that happens in the human body. So within the human body there are several different bodily functions that rely on the use of mass transfer, because ultimately without these we simply would not exist. So the first one is the purification of blood within the kidneys. So toxins are moved and transferred from high to low concentrations. They purify and clean the blood. You have the diffusion of gases through the lungs. So the only means of getting the oxygen into the body and getting the carbon dioxide expelled from the body is the mass transfer of these gases, and it happens in the lungs. Now you also have the transfer of nutrients and minerals through the cell membrane. Now granted, you aren't expected to be, a biologist, but in the context of the human body, mass transfer principles can also rely on what's called the selective or permeable membrane, whereby material, minerals and salts can pass through dependent upon their size. And again, this comes down to a difference in the concentrations. Now, as I mentioned before, the human body is dependent upon these mass transfer operations in order to function. And that's an additional point that you could make during the interview process, is that you understand the importance that mass transfer is in terms of your bodily functions. Now question number 3 is, what is the driving force for mass transfer? And I kind of alleviated to the response in the previous couple of questions. But in simple terms, the driving force for mass transfer is a chemical potential. And this can further be elaborated in a few different ways. For me, I like to describe mass transfer through a concentration gradient. So rather than the term chemical potential, I prefer to think of it as there is a change and a difference in the concentration from one point to the other. It's the same thing, but I just prefer that type of nomenclature. But it can also be defined as where chemicals move from high to low levels of chemical potential. So this one here is like the hybrid of both of these, because it's mentioning the high and the low levels, but it's relating it to a chemical potential rather than a chemical concentration. Now, like heat transfer when it comes to certain principles, mass transfer has their own dedicated set of laws and correlations. So in heat transfer, which we have a full video exactly the same as this for 10 interview questions on heat transfer. I'll put a link in the description to that, and you can check that one out. With heat transfer, we have what's called Fourier's law, whereas in mass transfer, we deal with Fick's law. Now the question here is, and this is a very, very common question, is define Fick's law of the diffusion and state the mathematical expression. So sometimes your interview might give you, a piece of paper and a pen, and you will be expected to know certain correlations off by heart. Now Fick's law states that the flux of a diffusing compound, and we'll use compound A as a reference, within the Z direction within a binary system of A and B is proportional to the molar concentration gradient of that particular system. Now the mathematical expression for this is given as J, and now sometimes you'll just see it as J, but here I've got the subscript A. And the reason it's subscript A is because it's dependent on component A. So A is my reference component. Now minus dAB is the diffusivity of A through B, and dCA is the change in the concentration, and dZ is the change in the Z direction. So you will notice there is stark similarity between mass transfer and heat transfer. The key distinction here is that instead of it being dt, it's dC because it's a change in the concentration. Now question number 5 is, how would you define or describe mass flux? Now mass flux is simply, or the mass flux of a species is essentially the mass of that given species which passes through a given area per unit time. So how much of that particular material has passed through a specified area of unit per unit time. So whether that's in seconds, whether that's in minutes, whether that's in hours, so forth. And is represented by the J, or in this case the JA from the previous question, in Fick's first law. So that is what the mass flux is, i.e. how much material passes through a specific area per unit time. Now when we have 2 or more dimensions that are used, the mass flux, just like in heat transfer, will become a mass flux vector. And this is by the inclusion of the gradient operator of this upside down triangle per se. So that's just a key thing to note, is that the Fick's law formula we've seen in the previous question is predicated on a one-dimensional model. If you want to go to a multi-dimensional system, you will have to relate it in terms of vector quantities. Now number 6 is, can you explain the Whitmans two-film theory? So within mass transfer there is a lot of fundamental theoretical applications and phenomenon that is very, very common within the setting of a mass transfer interview, or an interview that's going to encompass some amount of mass transfer. And you can expect to discuss and talk about Whitman's two-film theory. But in essence, or in summary, the theory aims to explain that when a gas and a liquid come into contact with each other, the gas-liquid interface is formed. So where the gas and the liquid meet each other, that meeting point is called the interface. Now within the interface, the gas is then transferred through the interface into the liquid by molecular diffusion. So that's when the gas literally enters the liquid, but it must pass the interface. Now the assumption of this particular theory is that stationary conditions apply, we have a laminar flow regime, and an instantaneous balance is established at the interface. Now if you can recite these assumptions in Whitman's two-film theory, I guarantee you will be well ahead of every other candidate that goes for that position. Because understanding the assumptions really highlights that you know and are highly familiar with how the theory is actually being built. Because if we think about it in terms of a laminar flow is very easy to predict, or it's easier to predict than turbulent flow. Turbulent flow, we cannot predict the behaviour, whereas a laminar flow regime allows us to base our system fully on an instantaneous balance being established at the interface. So these are all interconnected to each other. So simply by mentioning that what the Whitman's two-film theory is predicated on will put you well above everybody else. Now, another thing is we can relate this to a very common figure, and the figure here is this one, taken from the citation back in 1923. So this is the original concept for Whitman's theory, and it's basically showing you that the bulk of the gas here and the gas film meets, this is the interface here, meets the liquid film at that given point. So between the dashed line here and that dashed line, so that's at the gas side and that's the liquid side, that is the two films and the interface stuck together. And this is the point here that diffusion starts to take place, molecular diffusion into the bulk of the liquid. Now, the overall resistance to the transfer lies in the existence of the two very thin films on both sides of the interface. So that's through the gas and the liquid film. That's where the bulk of the resistance lies. Now, question number 7 is, what factors affect gas transfer coefficients? Now, this is getting quite specific because a lot of the time in interview questions, they might ask a very technical, industry specific question, which I have, there's a few different video tutorials and blog posts on technical interview questions for chemical and mechanical engineers. I'll put a link in the description to that, and you can check that one out if you're interested. But here, what the interviewer is probably looking for is, do you fully understand the influence and the factors that affect mass transfer operations within gases? So the kind of things that you need to mention here is the operating temperature. Gases are highly influenced by the operating temperature and in conjunction the operating pressure. The concentration of the gas, because remember, the driving force for mass transfer is a concentration gradient. So these factors will indeed affect the gas transfer coefficient. Now, I've included this one here, which is the nature of the hydrophobic substances. And the reason I'm adding this in is because if you can provide this in an interview and then provide the context to say that this is most notably for oxygenation of wastewater systems, then wastewater is a very prevalent and upcoming industry that is getting real emphasis, just the same as the renewable energy side, sustainability. Wastewater clean treatment systems are highly sought after. So this tells the interviewer that you are aware of current affairs as well. So just a nice extra addition to make you stand out from everybody else. Question number 8 is, can you explain surface renewal theory? So again, there is a plethora of different theories out there, but surface renewal theory is basically when the eddies of a fluid, so the eddies is like the vortices that form in a turbulent fluid mixture, the eddies of the fluid at this interface are exposed to a varying lengths of time. So the eddy will exist and be exposed for different time periods, maybe a couple of seconds, maybe a couple of minutes, so forth. But each liquid element that occurs at the interface will have the same probability of being substituted by a fresh element, because ultimately the eddy will have to dissociate and a new one will replace it. But regardless of the element and where it is and for how long it's been in existence, the probability of it being substituted by a fresh element is exactly the same. And this is on the basis of the exposure, the time histories, and an age distribution for the surface element. These can all be calculated. And the mass transfer coefficient, which is to say how well this material will transfer, is proportional to the square root of the diffusivity regardless of the nature of the surface renewal rate. So we have this kind of proportional but disproportional system taking place between these variables. Surface renewal theory is quite abstract, it's quite difficult, but this type of explanation, it will be enough for an interview style question. So if you get this kind of question, it means you're going for probably a fairly heavy mass transfer operational job. Number 9 is, what is liquid entrainment? So liquid entrainment is basically when you have high gas flow rates and small liquid particles are then carried, basically because the gas is has so much energy, it carries the liquid particles and rises them from the gas from the plate below. So this usually happens in like distillation columns or separation columns. And the gas will carry the liquid over to the plate above, and that is known as entrainment. And a pictorial representation here would be something like this, whereby in the red section you have entrainment taking place, because you can see that the liquid is being brought up with the gas, because the gas is has too high a flow rate. And because of this, ultimately the consequence is going to be that it will reduce the concentration per plate, because that means the efficiency of the tray will decrease as well, because where you should have, say, maybe 90% vapor, you might have only 85% vapor. So your tray isn't performing to its optimal efficiency. So entrainment is a negative thing when it comes to especially distillation. And then the final question is, what is Morphe efficiency? Define and state the equation. Now, when you're in an interview and the interviewer asks you to define and state an equation, that means they want you to pick it apart piece by piece. They want you to define each of the elements and explain the interaction between them. So this is when you probably need a pen and a piece of paper, and you're going to need to know your stuff. So that's why we kept this one to the end. But Morphe efficiency is essentially the efficiency of any single plate based on the vapor phase composition. So it's not the liquid phase. The Morphe efficiency is based on the vapor phase composition. And the equation is fairly straightforward, but it's given by E subscript mg, so that's Morphe, is equal to yn minus yn plus 1 divided by yn star minus yn plus 1. Now, if you were to state the equation, but simply did not explain what each of the variables are, then you probably would fail this question in an interview. Because ultimately what you will have to do is you will have to show you know what the distinction between each of these three are. So y star n is the value in equilibrium with leaving liquid concentration, and that's given by xn. So although these are y because they are for vapor, the x denotes liquid, the y star n value is the equilibrium value for the leaving liquid concentration, whereas yn is the average composition of the vapor in the leaving plate, and yn plus 1 is the average composition of the vapor in the entering plate. So again, it just depends on how or when you build the distillation column, what the nomenclature of the column is based on tray by tray. So normally what you say is the tray above would say be yn plus 1, the tray below would be yn, and so forth. So that's what they're probably looking for in that type of question within an interview stage. They wouldn't want you to go into copious amounts of detail, but enough to highlight the equation and state what each of the variables actually mean. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in giving you some detailed answers to probably some of the most common mass transfer interview questions. This is part of a series of detailed interview questions for mass transfer, distillation, heat transfer, and so forth. So if you like this video, please consider liking and subscribing to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we look forward to seeing you in another video.